Hello and welcome to today's webinar. Great to have you join us today. Thank you for taking the time out of your busy schedules to join us today. My name's John Pitcher, and I'll be presenting today's webinar around the technologies included in the Inventor Sheetmetal space. Accounts, to start off with, Accounts is a fully owned subsidiary of the French B2B services group Monure. Founded in 1906, the Monure Group operates in construction, industrial and agricultural sectors. Accounts was established in 2018 with a vision to become a leading partner for digitisation of the construction and manufacturing sectors. Today, through its Partner to Build Smarter strategy, Accounts is a major global service and solutions provider to its target industries. At Accounts, we're dedicated to helping the construction and manufacturing sectors realise their digital potential. Our proprietary and purpose-built Be Smart software seamlessly integrates with an extensive network of world-class technology partners. With one of the largest professional service teams globally, we're dedicated to the industries that we serve. We provide comprehensive services that cover development, integration, implementation and training, together with a full suite of advisory services. We take a holistic approach to digitalisation to provide your business with the right problem solution fit. So a couple of things about myself, just to introduce. I've been in the CAD industry for around 18 years and working in the Autodesk channel. Prior to that, I spent 20 or so years in the manufacturing sector, working as a fitter machinist, focused mainly in the CNC space. I was involved in various aspects of engineering, hydraulics, pneumatics, general engineering, and a few years in the food and beverage industry. In my current role, I'm a technical support lead for the Accounts ANZ team. I manage our support service, and as an Autodesk certified trainer, I lead various training classes for several of the manufacturing applications, mainly Inventor, Fusion 360, and AutoCAD. I also spend some time in the additive manufacturing or 3D printing space, more as a personal point of interest than anything. So what do we plan to cover today? Well, we'll start out by covering some sheet metal basics and just giving everybody a bit of a heads up on some of the general terminologies that you might come across. We'll chat briefly about different types of materials and sheet and plate design. We'll be talking about some equipment as well, as in it's probably important to understand how sheet metal is formed, often using brake press type machines. And we'll chat briefly just for a few minutes about that as we start out. Obviously, some of these processes impact fairly majorly the way that we design and manufacture components, and certainly being able to design components appropriately and working within those parameters is an important thing. Following this, we'll talk about some other elements of sheet metal manufacturing. Some of you may have come across the tools like turret punches or fly presses or coining rollers. Obviously, there's many ways of forming sheet metal, and today we'll just briefly look at the major ones of these, so predominantly just folding and bending sheet metal, with the intention of showing you how an engineer can design products and utilise Inventor's amazing array of sheet metal tools to come to a great result and to develop your components as per your requirements. We'll then move into a live demonstration and we'll explore some of the tools inside of Inventor, concepts for working with the sheet metal environment. We'll talk about sheet metal parameters, defaults, modelling concepts, and we'll look at some sheet metal punches. You may have come across these in the past. They are .IDE files, and we'll certainly look at some other elements like dxfing out of Inventor to create files that are ready for your laser cut, water jet cut, or profile cut machines. And if time permits, I'd like to have a brief look at the nesting functionality, which is a relatively new add-in for Inventor, where we can basically take a series of profiles and run them across a sheet of a particular size, whether it be 2.4 by 1200 or whatever it might be, to create an output that's ready to go straight into our production environment. So like I said, first up, let's kick off and just talk about some of the key technologies and the terminologies that we're going to come across as sheet metal engineers and the type of things that we're going to be working with. Again, not essential to know, and this is more of a general introduction to sheet metal than an Inventor sheet metal subject, but sheet metal is obviously a fairly big subject, and we obviously need to appreciate the need to get all of these items right and to understand the various functionalities here. So to put it simply, there's three main types of bending with sheet metal. We tend to use three main terminologies. There's what we call coining, which some of you would be familiar with. If you're a coin collector, for instance, that's where that terminology comes from. When you're coining something, you actually stamp that part into a male and female die, or punch and die effectively, and that forms that part. As you might be able to understand at the top of the screen there, we've got a part that's quite a complex geometry, and that would have been stamped and pressed into a mold effectively, or into a female and die with a male component that potentially punches holes and does reliefs and things like that as well. The other main areas that we might use a brake press for are for what we call air bending and bottom bending. So bottom bending is slightly different to air bending in the sense that with a bottom bending type situation, we tend to use a functionality where basically the die runs into the base of the punch, or the knife edge runs into the bottom of the part and fully compresses the material into the V bottom of the die effectively. The other method, called air bending, is much less demanding on your tooling, where basically rather than compressing right into the bottom of the die, we bend to a certain angle, but we always leave a slight air gap to allow our material to form, and we can work through with each of those elements. So we'll be talking a little bit about some of those functionalities, and obviously there's advantages and disadvantages. Air bending obviously being the kindest on your tooling and taking the least amount of pressure from your brake press. Bottoming type environments use slightly more pressure, and obviously coining uses the most pressure, but potentially is the most reliable because it gives us an exact part effectively. Where with air bending, your pressure on your plate and the spring back from the part will obviously be slightly greater. Obviously, most manufacturers would use a combination of these in their general manufacturing processes, depending on the required tolerances, etc. So there's a lot of technology involved here, and it's certainly good to understand what's going on here, especially when we talk about materials that are have a high tensile strength, so the likes of titanium or other tool steels. When you're bending those, obviously we need to be very conscious of things like fatigue or cracking, or potentially causing weaknesses in our finished part. And again, that very much is dependent on the type of tooling you're working with, and also the type of equipment you're working with. So depending on your brake press type. So let's talk a little bit about brake presses. Obviously, again, when we talk about modern brake presses, there's a lot going on in this space. And again, there's sort of four main types of brake press. We've got a nut-stop hydraulic, we've got a hybrid type brake press, we've got an electric brake press, and a CNC brake press. Now, obviously, we can have a CNC that is hydraulic. They're mainly CNC brake presses are electric, but so electric drive motors that create the pressure for us to cause the forming of our sheet metal part. Again, depends on the type of components you're requiring and what your workflow is. So not to go into huge details, but nut-stop hydraulic are probably the older type of machine, I suppose. These have been around for many years, and yeah, some of you may have even seen slightly older ones of these with, like I said before, a fly press, where you're using a heavy weight to actually create the impact or the impression in your particular component, or to create your bend. So at the end of the day, it really does come down to what you're trying to achieve and what you're actually working with. So there's quite a number of different options. The other one that we do tend to see in the hydraulic space is a synchro hydraulic, which has a digital control system. So again, a bit of a sort of a hybrid type environment, where you've got a combination of electric and hydraulic type movements. The main benefit of electric and CNC type brake presses is the safety factors. Obviously, when you've got 500 tons of hydraulic pressure, we've got a cylinder or two and some very high pressure type situations, and there's obviously liabilities and things related with that, and safety elements that we need to be aware of. The great thing about electric is obviously we can put lockouts and things like that to ensure people don't put their fingers in the wrong place, and we don't end up with ongoing issues or safety challenges in that regard. So again, lots of different methods of forming sheet metal. And look, we won't go into this in huge detail, but another big factor in the sheet metal world is obviously what we call the K factor. Now, for those of you that have been in the industry for some time would be very well aware of how the K factor behaves, but effectively it's a theoretical center line through the middle of a piece of plate or sheet where the material maintains its original length after you bend it. Obviously, when we bend material, the inside of the bend compresses the material, the outside of the bend stretches the material, look, at the end of the day, the final result that we get out will depend on how we set that K factor, and we'll talk about this when we go to our live demonstration shortly. This obviously has quite a major impact on our sheet metal model and our output, and how that theoretical center line is actually going to work. So again, depending on the ductility of the material that you're working with, again, very high tensile materials and very soft and plasticine-like materials, if you like, to use a simple terminology. So the likes of aluminium flows quite nicely when we bend it. So you'll notice the K factor there will be slightly different. So again, depends a little bit on the process you're using and also the nature of the material that you're working with. So this is quite an important thing to understand when we're working with sheet metal models. Now, there's a bunch of other technologies and terminologies, things like bend radius, bend length, bend to bend distance. We've got kerf factor and a whole bunch of other terminologies that we don't have time to go into today. We do need to keep this presentation under an hour, so we'll move on to some other elements. Now, Inventor's sheet metal environment has been around for quite a number of years, and there's been some really nice developments to it over the years, with a whole bunch of extra technologies and tools added to that to give us the best option. And certainly Inventor 2025 has some really nice functions, and we'll look at some of these a little later on as to how we might work with the Inventor sheet metal space and how we might produce our Inventor components. One of the main changes in the Inventor space is the change to a lot of the dialogues. For those of you that have been using Inventor prior to 2024 and 25, you'll notice quite a change to some of the dialogues here. There's quite a few nice little functionalities there. Obviously, they've modernised a lot of this and made some extra selection options and just changed the look of a lot of this. So just to try and make the workflow a little bit more fluid and a little bit more consistent. All right, so that's a bit of an introduction. What I'd like to do now is swing over to Inventor and talk to you about some of the functionalities, and we'll certainly be looking through some modelling environments and some of the types of situations that we might come across when we work with Inventor sheet metal modelling. What I might just do is go ahead here and open up a standard sheet metal file, just to give you a bit of a look at how this works. And again, apologies to those of you that have been using this for some time. This will probably appear a little basic, but the sheet metal tools inside of Inventor, obviously we've got quite a raft of specialist items here that are related to the sheet metal environment. But really, before we even start, we need to set up some configurations. One of the main ones, obviously, is the material type. So inside of Inventor, obviously, we've got a range of materials that we can select from. And if we choose to use the Autodesk material library, we obviously get a much greater list of materials, all sorts of different grades of aluminiums, etc., etc. So there's quite a lot going on in this space, and this is an area that's certainly worth exploring and having a good look through. So once we've assigned, let's say we're going to assign stainless steel, the other key thing is the sheet metal defaults. Now, the sheet metal defaults in Inventor are really, really important to us, because what this is doing, it's allowing us to set up primarily the material thickness. The other thing that we set in here is that K factor that I mentioned earlier. Now, like I said, that will be dependent on the tensile strength of the material that you're working with. So obviously, if you're working with copper, you're going to have a very different K factor to if you're working with titanium or stainless steel or some other type of material. Now, the sheet metal defaults are very, very critical, and we'll certainly talk about how that all works. But if we jump into this environment, there's quite a large bunch of settings, and in actual fact, there's quite a lot of math in the background here of the Inventor system. And obviously, we can preset things like how we would like our corners to look. So when we fold two sides of a face, obviously we can change the way that we would like to, and again, depending on what type of downstream processing we're working on, things like fatigue or whatever are going to impact the way that we drive some of this. Now, back over here on the left side, if we go to this particular area, we can see in here as well some other information about the mathematics in the back end of Inventor that are going to dictate the way that the system behaves. Now, as I mentioned, the K factor effectively is this red line through the middle of the part here that when we fold it, it maintains its original length effectively. As you can imagine, this material in the middle here compresses, and this material on the outside of our bend is actually what's going to stretch. So there's quite a lot going on here, and it's good to understand some of the various elements of that and how that all works, but that's probably a subject for another day. So I'm going to set my material thickness to 1.6 millimeters. This is obviously a very common size for any types of brackets or anything like that. So that now controls my thickness. Now, the other really important thing with the sheet metal type environment is there's a bunch of preset parameters. So when we launch into the Inventor sheet metal space, as you can see here, we've got a series of 8 or 10 different parameters that are predefined. So these parameters here are all driving based predominantly on the thickness of the material, as you can see, but there is a couple of others as well. Things like bend radius are obviously going to play a part in this particular space. So we can set a lot of these. Obviously, we can set tolerancing in here. We can do a whole bunch of things as well, and some of those items and elements can work within that system. So at the end of the day, when we're working with sheet metal, we just need to understand that we've got these parameters set. So when we start modeling, and again, the modeling process is very similar to what you'd be used to within any of your modeling type environments, where we're perhaps going to create I'm going to make a little bracket here just as a bit of an example. And basically from here, once we've got our shape, we can create a face from that. And automatically this face will be 1.6 millimeters thick. Okay, so when I create a piece of material, and again, because I've picked stainless here, so this is a 1.6 stainless steel component now. Now, what you can do is obviously set up different templates, and accounts can certainly help with that. If you want to set up a bunch of templates, let's say you do a lot of work with 3mm material, with 5mm material, 10mm material, maybe 12, 16mm plate, you can set templates up so as each of these items are going to be usable as a separate template. So I'm just going to call this a G bracket, and we'll actually use this a little later on. Let's not do that. Let's do a save. Would be smart. So we'll just call this okay. So what we're going to do now is just look at some of the very basic tools. And again, there's a lot of tools in here. We don't have time to go through all of these today. We do run training courses in the sheet metal space, and I might talk about that a little later on as well. We run a 2-day course that assumes you've got a fair bit of knowledge about Inventor that focuses predominantly on the sheet metal tools. But effectively, when we create, for instance, a flange or something like this, we can set up the height of the flange. We can set up things like the direction it goes, whether it flips this way, this way. There's a bunch of different tools here for the position of the bend, depending on how you might like to have that function. So we can create flanges based on a whole bunch of criteria, and yeah, certainly we can work with each of those type models as we go through and to create different components. So the long and the short of this, though, is that obviously we can create whatever we need to create. I'm just going to create another little process here where I'll actually jump in and do a little slot through the middle of this part. So I'm going to let my inventor snap to the midpoint here and create a slot across this particular part like this. For my bracket. Now, a couple of interesting things when we're creating sheet metal components. There's some, and again, I could have given that sizes and things like that, but I'll just save a bit of time there. But effectively, if we go and do this as a cut now, we can either cut through the material and pick OK, and Inventor will, as you would expect, because there's no material out here, it won't actually do any cut. But if I go in here, I've got an option here to cut across the bend. And what this effectively does is it wraps my profile around my 3 flanges in this instance and allows me to create a shape like this. So we can actually wrap, kind of cool functionality, because what it's done, it's taken the overall length of my part. The other thing I can do as well is if I untick this and pop a value in here of 40 mil or something like that, I can obviously just cut straight through each of the flanges there. All right, so like I said, lots of different options in here, and just to perhaps point out a couple of the other nice little options, and we will explore others as we go through, but one of the other kind of cool little options is in here, if I want to put a hem on an edge to give it a little bit of stiffness, we can roll an edge back on itself like this. In actual fact, in the hem tool, there's 4 different options here. We've got a single hem, we've got a teardrop, we've got a double rolled hem as well. So if I was to pick this edge, Inventor will roll this completely around on itself like so. So at the end of the day, creating components using the sheet metal tools, and again, this is only a very basic part, are very simple. It's certainly not rocket science to build sheet metal components, and I think you'll find the workflows and the tools are all quite valuable and quite simplistic. Obviously, once we've developed our model, we can jump in here and go to our flat pattern view. So there's a view of our model in its unfolded state, which is kind of cool. And one thing that I tend to use at this point, if I'm going to go and send this file off to my laser jet machine or water jet machine or whatever it might be, if I right click on the face of this machine, you'll notice I've got of this particular part, I've got an option here to export the face as, and that will allow me to output straight out to a DXF file. So that's a very common format that most laser cut, water jet cut, profile cut machines will actually read in. So we can very quickly create a DXF that's ready to be utilized in that sense. So I'm going to jump back here and just save this part. We're going to use this part a little later on in our demonstration. But one other thing that I'd just like to briefly mention as we talk about this, and again, we're going to go through a couple of other little practices. So there's a whole bunch of flanging tools. We've got obviously a standard flange. We can create a contour flange. So if you've got a flange that is a particular shape, we can simply sketch that shape and then create that flange to whatever depth we would like. Next up, let's have a quick chat about this lofted flange option. I'm going to jump into a new sheet metal part. This is a kind of cool function because if I was to go and do a couple of sketches, and again, I'm going to do just a standard rectangle here, and I'm not too fussed about the sizes. Let's make this 600. So let's say we were going to make a canopy for maybe over the top of a stove type or something like that. This would be the way that we might do that. So once we've created our shape, and again, I did a bit of I don't think I quite selected my, I might just fix that. I don't like purple sketches. Purple sketches have a bit of a habit of bringing us unglued later on. So I'm going to coincidentally constrain that with my origin. I should have done that by default, but nonetheless. What I'm going to do now, though, as part of this particular scenario, is we're going to create a plane offset from the origin plane, and we'll just come up, let's say, by 600 mil. And what we're going to do is now do a sketch on this particular plane. And I'm just going to draw a circle on here. And again, I'll make it a 300 diameter circle. Again, I probably should constrain that, but just for the sake of time at this point, and I notice we're already halfway through our webinar, so let's keep things moving. What I can do with this particular tool is I've got an option here to create what we call a lofted flange. So this is really good for a squared around transition. And for anybody that's ever worked in the sheet metal space, you're probably aware of the requirements to do these, especially if you're in the industry of doing things like canopies for fish and chip shops or anything else that might be product flow, like a ducting type environment or a hopper or something like that. Now, just one point of note: when I select this, I've got I basically can pick my two profiles, and then I've got a couple of options here. I've got the options to do this as a die form type squared around transition, where I might be forcing a piece of square tube into a round mold effectively. So that would be one way of doing it. But the other more common way is to use, again, a brake press to create a bend line. So we end up with a series of flat sections around here. And what this dialog is actually telling me is that the deviation from my drawn 300 diameter circle to each of these flats is a maximum of 0.5 millimeters. If I was to change this to 1 millimeter, that would reduce the number of facets. So you can see the facets actually got a lot wider here. So if I'm happy with that, and there's a whole bunch of options obviously in the back end of this that we can set up as well, but effectively there's my squared around transition. That's all looking fairly happy. I'll just turn off my work plane because I don't need that anymore. Now, what about if I want to unfold this? Well, at the moment, because this is a closed shape, Inventor will not let me unfold. In actual fact, if I went and created a flat pattern of this, basically nothing would happen. But effectively, what I can do is create a rip. Now, in the rip command, we've got the option to do a point-to-point rip. And if I wanted to rip from the midpoint of this edge up to this point up here, Inventor basically creates a little cutaway. And as you can see, if we zoom up here, we've now removed a little segment of material, which is kind of cool, because what that means now is that we can go in and create a flat pattern of this squared around transition. Okay, so there's a flat version of what my squared around hopper might look like, or my canopy, whatever it might be. And again, right click here, export the face as DXF, and I can go out and laser cut. So inside the DXF as well, if you've got somebody that knows a little bit about laser cutting, often they can scribe these lines for you. So they can turn down the intensity of their laser and scribe the bend lines for you, and that's all well and good. Now, a couple of little things in the flat pattern mode. So in sheet metal, we obviously have two modes. We've got flat pattern mode and folded model mode. In here, I can go in and ask Inventor for a proposed bend order. Now, for anybody that's ever done any work in sheet metal, you'll know that you never start at one end and work your way to the other end, because by the time you get to the other end, the last 10 bends will not be able to be done. So Inventor actually comes up with a method of what it suggests as the most likely order in which you might choose to create this particular part. Now, we can manually override this. We can go in and set this one here as bend number 8 and this one here as bend number 10. We can change those, and obviously that will be dependent again on your tooling, the type of machine and equipment you've got, etc., etc. So yeah, kind of cool that we can go in and set each of those environments, and we can go in and set those bend tools. Now, within this particular situation, if we wanted to create like a little lap joint in here to allow us to work with this, we can simply create a little flange here, and we could say this flange is a 90-degree flange, and maybe it wants to be, 3 millimeters high or something like that. So we create a little flange that's sticking out from the part there, as you can see. And then I could create another reverse flange on this one out this way, and maybe we'll make this one 15 millimeters or something. Oops, 150 millimeters. And we could now go and solder or rivet or silicon or whatever we'd like to create a nice little lap joint within our squared around transition. So yeah, kind of cool that we can do that. And again, if I go to my flat pattern, you'll notice on the end here now are those two little bends that we just talked about. Now, the real deal breaker for me, and again, for those of you that have done any work in this space, you'll know the complexity of finding out what each of these bend angles is. But in Inventor, it's a real cinch. So I'm just going to save this part and call it SQ R&D. So let's save that out as a squared around. And what we're going to do now is just for a quick 2 seconds or 5 minutes maybe, just have a quick look at how this might transpose into a drawing type environment. Cool thing about Inventor, obviously, for anybody that's working with the software in Inventor, creating drawings is very much a cinch. It's a very quick and easy situation, and we've got all sorts of options here for creating quite complex drawings in a very short time frame. The cool thing about the sheet metal space, though, is that we've got an option as well to put a copy of our flat pattern onto our drawing sheet as well. Okay, so this is very valuable to us because, again, trying to calculate each of these details obviously would be a little bit complex. We can go in and do things like retrieve model dimensions, so we can bring in the dimensions that we've got here and keep those on the drawing. So Inventor has some really nice little tools for allowing us to create dimensions in an automated fashion. But to me, the real showstopper as such is that we can, with this flat pattern here, how do I know what the bend angle is for each of these parts? Well, Inventor in its amazing capacity allows me to create a table, and as soon as I select this view, in actual fact, what Inventor will do, it will bring in a bunch of eye properties, which some of you may be familiar with. So it's picking up the bend ID, the bend direction, the bend angle, and the bend radius, and it will put them nicely for me in a table. And again, that bend numbering system is there, but here's each one of those bends to 3 decimal places, would you mind? So again, it's just telling me what each of those bend angles is. I know when I first saw this, I nearly cried because I remember during my apprenticeship, we had to actually do one of these. They gave us a piece of cardboard and said, go away and make a hopper of some kind. And we actually had to sit down and physically calculate all of these angles. Yes, it was tedious, but it was a good learning process. And when you see how quick Inventor does this, it's quite an impressive sort of situation. So look, I'm not going to go into drawings in any other details. Obviously, there's a bunch of other things we can add in here as well. We can obviously add other information to the drawing and whatever else we need to do as part of that process. But yeah, I think that's quite a cool function. So we're going to leave drawings alone. I didn't want to spend too much time there. We have done other webinars in that space. So if you'd like to search for those on our channel, you'd certainly be able to find those. All right, one other little thing that I'd like to jump into now, just briefly. Again, I won't spend too much time here. One of the items that I did mention was that we can quite quickly go in and generate what we call a punch tool. So Inventor has an option for a punch out, or maybe like an indent, or a typical switch cutout or something like that. And what this actually does is it will allow me to pick from a predefined library, which you can add to, obviously. So if you've got a particular type of cutout that you'd like to place onto a sheet, Inventor comes with these typical D-sub or VGA type outlet connectors, which are kind of cool. But we can also do things like keyways, or something like a switch cutout where you've got a little tab on a particular item. And also there's a couple of emboss features where, in actual fact, this particular model already has a couple of these. You can see here that we've placed a little indent, if you like, or a coined embossment on that particular part, so we can actually go and place any of those items. But yeah, like I said, if I pick this one here and then I go and pick this center point, Inventor will place that cutout on my part. So we can very quickly create reusable punches. So if you're doing a particular type of cutout, if you're a switchboard manufacturer and you're putting a lot of mushroom switches or on-off switches or switches that twist to on-off, and you want like a specific little cutout, we can very quickly go and use the punch tool to actually allow us to do that. So as you can see here, we can configure these. So in here, you'll notice we can change some of the geometry sizes. You can rotate these around, so you can call them this. Again, depends how you build these. So we do talk about all of this in our sheet metal, in our 2-day sheet metal course on how to create punch tools and the different elements of utilizing a lot of this sort of geometry. So I'll just undo that one and show you very quickly. Again, one of these other punch tools, which is a little round emboss. If I pick like so, again, I can change certain things about that. We can pick up different things here. But if I pick like so, we can end up with a like a little coined emboss or a foot. Very easy to create these, guys. It's not rocket science. It's just a matter of creating the punch tool effectively as an eye feature inside Inventor. For those of you that are using eye features, etc., kind of cool that we can just very quickly go and generate our geometry from that. So again, some pretty neat little functions there for reusing shapes. So you want to maybe cut down on human error or potentially create a very repeatable type situation. What about in the assembly environment? Well, again, we've got a bunch of different options. This is a little hydraulic crimping tool that I've got here. And what we're going to do is just briefly talk about maybe how we can create for this panel. As you can see, we've got a lot of equipment on the back of this, and to put a bit of a scenario up, the operator found that sometimes he bumped these fittings and then they needed to be reseated or resealed or whatever. So we're going to create a little shape for the back of this, like another little cover effectively, and then we'll hang. Also, this operator wanted a little bracket for his air gun to hang on, so he's got that nice and handy when he needs to blow his mold, his crimping die out to be able to crimp his fittings. But first up, what we're going to do is just explore how we might go about creating a component inside of the that particular system. So I'm going to activate the control panel subassembly here, and we're going to do a little bit of work on this. So first up in this space, what I'm going to do is create a plane offset from this edge of this particular face, and maybe we'll offset this back 150 mil or something like that. So we can just, obviously, for those of you that are aware, we can just click and drag this and set the offset. Oh, that's interesting. This is an imperial model, but the cool thing about Inventor, we can obviously type in mm in a imperial model and end up with a quite a nice, well, that might be a little bit far. I'll just edit that back to 110 mil or something. All right, that will do for us for now. So what we're going to do now is we're going to, in the context of our assembly, we're going to create a part. Okay, so I'm going to actually go in and create a new part, and we'll call it panel cover. Okay, and as you can see, Inventor's going to want me to create a plane for that particular. Sorry, I did that plane in the wrong environment. I need to create my plane now. So let's create the plane based on this. Actually, we should be able to select. Let me just do that again. We'll create the plane back here, so it clears the. And we're going to do a sketch on this plane. All right. Now, when we come to creating components, as I'm sure some of you would be aware, obviously, our best friend in this type situation is our project geometry tool, where we can obviously create some relationships through our particular parts and work through each of those particular scenarios. So in actual fact, what we might do is, yep, that's fine. So what we're going to do now is create a into the sketch and just complete this by create a couple of lines up here just to make this look pretty. All right, so we've got our shape now, and effectively what we're going to do is we're going to create a face out of this. Now, this particular part, when I created this part, I missed a step, and I sort of intentionally did this because what we can do at any point in our modeling process is we can simply convert this to a sheet metal part. And what that will do is allow me to then go and set my sheet metal defaults. And maybe for this particular situation, I'm going to make this out of 2mm material. So we can go and set, obviously, at any point, the material that we want to use, etc., etc. So when I created my new part, I should have actually been a bit more conscious, but what I did there was I picked that particular item. So we're going to create a face now out of this shape that we've projected. And we'll create our face like so. So there's the start of our particular component. Now, a couple of little things here. So there's the start of our little cover that we're going to place on here. So let's create a couple of little flanges. And what we're going to do is we're going to set a flange on this edge. And one little tool that Inventor, which I find is really underrated here, when it asks me for a length of the flange, and you can use this wherever you're entering a value, you can simply go in and measure to pick the distance for the length of that flange. So if I set this face here, and the fact that I want my flange to come up and meet with the back edge of my particular component here, you can see there that we end up with a very nice little flange. And I'm going to go in here and add another flange here and here to create my cover plate. And I'm happy with that. So very quickly, we can generate some pretty cool functions and some quite quick shapes here. So if I pick this edge, and this time, rather than this distance, I want to go measure. And again, I'm going to pick the inside face and the edge here, and that will give me a nice result there. All right, so we very quickly created a nice little cover there, so our operator is no longer getting self-tangled up in the workings of our particular of our shape. And what we'll also do at this point, and again, this is more of a bit of a side element, but if I was to go in and place my part called AG bracket at this point, and I want to place this into my assembly, and what I'll do is just quickly assemble this with a couple of constraints. So let's pop a constraint or two in here just to make this working with my spacebar. I don't have my spacebar sitting on this computer at the moment, so having to manually orientate and losing myself a bit here, but anyway, we'll get there. So we're going to attach pop this here. We'll do a little wash constraint between this edge. All right, so there we go. We've got our little air gun bracket, and we've now got our operator will be much happier because he's not getting himself tangled up in all the hydraulic lines, and he's also got somewhere to place his air gun now. So let's do a quick save on this particular assembly. All right, so look, like I said, we could have spent a lot more time there and done a bunch of tools, but I'm a bit conscious of the time. So so moving into the next area, and I thought I'd just do a quick little 5 minutes on the nesting side of Inventor. Now, this is a very nice functionality that I'll quickly bring to your attention. Inside of your product design manufacturing collection, you do have access to the nesting tool, which is a a really nice little tool that that we can use to create nesting studies effectively. So the amazing thing about this particular tool is that we can work with this, and I'll just give you a quick look at where you can find this if you've not used it in the past. The nesting tool is available for you to download from within your Autodesk account. So if you do have, if you jump into products and services here, you'll notice it lists all of your products that you're assigned. Obviously, I have a number of these, but if we scroll down a bit down through here, apologies for the delay, but yeah, we've got this Inventor Nesting tool. So this particular tool is an add-in for Inventor, and I'd like to now give you a bit of a rundown on how that works, just for 5 minutes or so before we wrap up. And I should have said earlier, guys, please feel free to use the Q&A inside the Zoom window, and yeah. Just to work on, if we will have a few minutes for questions and answers at the end if we're left with any time. So quickly, how does the nesting system work? Well, quite basically, it's quite a powerful little tool in the sense that once you've got the add-in installed, and you'll see this under your add-ins here, it'll just pop up as an option to use. So Inventor Nesting, I've installed that on this particular machine. So the nesting application is designed to allow you to do a study on how most efficiently you can create a series of brackets or a series of flat patterned items and placing them onto maybe a 3 meter by 1200 sheet of plate. So effectively, the nesting tool is quite an interesting tool. You will notice once you install this, you actually get a 5th type of template. So obviously we've got part, assembly, drawing, and presentation templates. We've got this 5th one down the bottom here called a nesting, .inest file. So just to briefly give you a rundown on how this works, if I open this particular file, what this does is it allows me to create a study based on some parameters and some settings that I might choose to use. Now, before we get started into actually bringing in the parts, and we're going to use our sources button up here to do that, where we can go and select either, would you believe, we can pick up a bunch of IPT files and say, I want these particular 5 IPT parts laid out on a 3 meter by a 1200 sheet of stainless steel or whatever it might be. Before we go to that level though, guys, it's worth spending a little bit of time in this area here under this process library, and particularly under this packaging area where we can set up a bunch of materials. So if you work with a lot of, like I said before, 1.6, 3 mil material, 5 mil material, you might want to add a series of these, because what Inventor does, when you add a bracket to your nesting study that's made out of 3 mil material, it will automatically pick up the material that you've selected here. Now, I haven't set any of these up, and obviously we could go and set up a whole library of material thicknesses that we commonly use. And what Inventor then does, it looks at your part files and says, oh, this one's made out of 3 mil plate, that one's made out of 1.6, that one's made out of 5 mil plate, etc., and it will so lay them out on the actual model. Obviously, we assign the material type as well. The other thing that we do in here as well is specify the type or the size of the plate. So like I said, if you're working with a, let's say we're working with a 24 by 1200 sheet of material, we can obviously go in and change these sizes here to set up our stock size. And again, that will depend on how you operate and what your material types are. So normally what we would do is we would set the thickness and the plate sizes. And in actual fact, there is an option in here to set up like a roll of material. So if you're rolling off a roll of stock sheet, you can obviously do that as well. Now, the other quite important one, hidden underneath the manage area, we've got this providers area. And what this does is it allows me to search for particular files. So this isn't just limited to Inventor. We can actually go and pick up DWG files from AutoCAD. We can pick up DXFs. If we pick up an assembly file, we can actually tell Inventor to look at all the sheet metal components that are included in this assembly and place them into our nest study. Kind of cool, because what that will do in the instance of our crimping machine, it will pick up the 4 or 5 items that I've got there that are made out of sheet metal and apply them to our nesting study. Now, if we jump down to IPTs here, we've actually got 4 different options. So we've got Inventor Sheetmetal, we've got composite parts. Now, this is an interesting one because, and again, this is obviously a very much a growing area where you might have a composite panel that consists of a 0.6 mil thick piece of aluminium, then a 50 mil piece of styrene, and then another 0.6 like a fridge panel effectively. So you could actually set up a composite panel where you can actually have multiple of these type items as well. Inventor parts are our standard Inventor parts, and generic CAD will pick up files from a bunch of other CAD systems. So if you've got SolidWorks files, or you've got files from Pro Engineer, or you've got files from CATIA or Unigraphics or some other CAD system, the AnyCAD functionality will actually allow you to bring those in as part of the nest. So kind of cool. This is not just limited to Inventor. So we can pick any one of these and place these particular files. So what we're going to do is just start off fairly basic here. What I'm going to do is when we start a nest, basically we open up this sources area and we can go and select the files that we want to include. And Inventor will bring us up with our little area here and say, you know, where do you want to pull these particular files from? So if I was to go in here and pick up my hydraulic plate, which is my plate for my my little display panel, you'll notice I get a little error message, and it says here that the material that you've selected isn't in your library, and that's why I said it's so important to set up this process material library. Now, what it will do, it will resolve that and just say, well, I'm going to give you a 5 mil material, but what I haven't selected is the length and width of my sheet, so I would have to go back and do that. But nonetheless, let's to save time, we're going to go through and grab another couple of files. So inside here, we'll grab this little joist hanger, and we'll grab our bracket number 2. And we're going to pick this. I'll also add another source file, and I'm going to grab from here my little hydraulic plate. So let's grab this one as well. All right, so Inventor's found the materials and it's working on how it can best do this. Now, like I said, I haven't done all the background configurations just purely from a time perspective, but we could certainly go through that. That would obviously take us an hour or so to go through that. But effectively, if I OK this now, Inventor goes off and looks at those 3 shapes. So here's my panel with my dial on it and things like that. Here's my other couple of brackets here. And as you can see, it's found these particular items and effectively set those up. Now, what I can do in here, if I go to Nest Properties, this is where I can set the quantity for each of these parts. So let's say we want 15 of these, we want 20 of these, and we want 6 of these, for instance. Okay. And as you can see here, here's the material thicknesses that have been pulled in from my Inventor model. And if I now run my nest study, Inventor will go off and it's processing this in the background at the moment. So it's saying, well, what do you want to add a comment to this? So I could add some information here. It just calls it nesting study 1, and it goes off and builds in the background all the data, and it's going to lay out the quantity I required on my sheet of material and tell me how it can best interact with those. So as you can see here, here's the final product, and effectively it's come up with this particular layout. Now I can also, and there's a lot of configuration things that I haven't talked about in here, and we're probably not going to get time to, but just something that is probably on your mind is what about if you've got like a grain in your material and you want all of your stainless steel parts to be in a certain orientation to the grain? So what you can do is you can limit that and say, I want all of these parts to be 90 degrees to their original format. In actual fact, what Inventor picks up by default, interestingly enough, is it will pick up you can see the layout of these particular parts. When I go into the actual part file, it's actually picking up, this is the default orientation. So whatever the orientation of the flat pattern was, will be what is picked up in your nesting study. You can see this is picking that up according to whatever that orientation was set. Now, what this does, it will tell you the efficiency of the layout, and if we're using this amount of material, it gives you some percentage feedbacks on that, and it will tell you how much material it's using. There's quite a lot of information going on here. So what can we do from here? Well, if I'm ready to say, yep, okay, I'm going to go and cut these parts out of a piece of plate, I can now go over to my nest here, and I can right-click on this nest, sorry, not here. We can actually get this out of the sheets area. So just give this a second. Just going to have a little think. And I do find sometimes Zoom does this to us, guys, when we're on a Zoom call. Sometimes the system wants to have a bit of a think here. But if I right click on this sheet, I can now export this directly out as a DXF. Okay. And like I said, for those of you that aren't aware, the DXF file can have configurations with it where you can set things like your bend lines to be laser engraved to a depth of 0.005 millimeters or something. So you can scribe those lines, etc., etc. So you can actually apply a DXF template to any of these files to allow us to work with that. Now, like I said, the nesting side of Inventor is quite a big subject. We could spend a couple of hours talking about this, no problems at all. And there's a lot going on in a lot of these configuration areas that I mentioned earlier, but that's a bit of a quick 5-minute rundown on how that sort of works and how that all functions. Like I said, it is a relatively new technology. It's a very, very clever technology, I think, that does a lot of really good stuff for us if we're working with that. Again, like I said, lots of things we can configure as to how you would like your parts to overlap or interact, or if you want, snap out sections or things like that, we can obviously do that as well. So that's what I had hoped to cover today, guys. I hope that's helpful. Like I said, there's quite a lot going on in the sheet metal space. It's a very, very interesting space. Like I said, we do run 2-day courses on the sheet metal side of things, and actually I'll pop this into the chat so you can all have a look at this link later. We do run a course. In actual fact, we've got one scheduled for Monday, but we do run these on about every 2-month basis. So it's a 2-day course that assumes you've got some skills in the Inventor space, and basically looks at each of those particular situations. So, and look, we do have a special going on our training at the moment. I believe if you there's a 40% off special, so you could jump onto any one of these courses if you book before the end of February, I think it is. It's quite a good value option for 2 days of training. So, look, I hope that answers your questions. Like I said, we will stay online for a few minutes and have some Q&A, but I realise we're up to our hour, so we will wrap it up at this point. Thanks very much for attending today. I hope you've enjoyed what you've seen. Please do get in touch if you've got questions on this particular technology, or if there's anything of interest to you that we can help you with. Email address on the screen if you'd like to reach out, and more than happy to chat further about this. So, yeah, I hope today's been helpful, guys, and please do pop any questions you might have into the Zoom chat option there, and I'll try to answer those as we go through. I will stay online for 5 minutes or so, and we can chat further about that. So, thanks again for attending. Have a great day ahead, and enjoy your weekend, and stay well. All the very best.